All right, so the focus of this video is going to be thinking about when you have molecules that have more than one H, which is going to be the case for almost always. Um, how do you know what is going to be the most acidic proton? If you put it in the presence of base, what proton is going to be removed? And we're going to kind of approach this from one of two ways. The first is going to be through pKa's. The second is going to be thinking of just purely about some themes around structure, and we're going to learn a mnemonic called cardio. So when we think about pKa is a value. It's a term that you can actually learn in general chemistry, especially general chemistry 2, and it refers to how easy it is to remove a proton. Things that are really, really strong are going to have really, really small, especially negative pKa values. A pKa value really, really high means that it's a much weaker acid. It does not want to give up your proton. So in many ways, think about that number of pKa as how much resistance you get if you're trying to remove that proton. If you have a really, really high pKa, so if we look at our small chart over here on the right, way at the bottom where we have just a hydrogen connected to a carbon, you have to do a lot of work in order to remove that proton. You need a really, really, really strong base. On the opposite side, where if you look all the way up at your hydronium, which is our kind of most common general chemistry acid, that's very, very easy to remove that proton, and it has this negative value for your pKa. Most organic stuff is going to exist in the positives, a lot in that kind of 5-10 range for common acids, and then in that higher range, that 20 to 50 for things that are a little less acidic. Now, on our course page through our learning management system, I have a handful of handouts that give a bunch of pK values for a bunch of different common functional groups or structures or features within a molecule. That being said, you do not need to blindly memorize pKa's. There's going to be some that we'll mention all the time. So a really common one is going to be the pKa of a carboxylic acid. We're going to see a lot of carboxylic acids in this course, and the pK is around 5. And there's going to be some common numbers that you're going to see again and again and again, but you don't need to blindly memorize. And that's going to be because of the fact that we're going to learn this mnemonic of cardio and just purely think about what the structure is rather than trying to find it on a table. Generally speaking, the pK of water is 15.7, right around 16. I'll often say 16 just to be a little bit easier. So if you have molecules that kind of have higher pKa's or lower pKa's than water, it can kind of help you see is water going to be a base or water is going to be an acid in that case. So 15.7 is kind of like a good threshold for kind of consideration just because of how present water is. Now, the main approach that we'll use, rather than just blindly memorizing a bunch of pKa's, is thinking a lot about what is the structure of your molecule, that molecule being HA. Now, there are going to be a bunch of different possible A's. If you think of a big complicated molecule, it might have 10, 20, 30, maybe even 100 different hydrogens. To try to figure out what is going to be the most acidic, one of the things that we'll often think about is what is the product that's formed. If you remove a proton from your base acid, you're going to form a conjugate base. The stability of that conjugate base is going to help us gauge how easy it is to remove that proton. If that resulting product, that conjugate base, is super stable, it doesn't mind losing that proton nearly as much. So that's going to be significantly more acidic. So one thing we'll often do is we'll look at that conjugate base and then rank its stability. Now, there is a mnemonic I've seen in a handful of textbooks here that is known as cardio. And cardio is a really good example of kind of our thought process between looking at a structure and then thinking about what's going to be the most acidic proton. So cardio is going to stand, the C in cardio is going to stand for charge. Do you have a positive charge or are you neutral? A is going to stand for atom. Those are going to be thinking about carbons versus nitrogens versus oxygens. R is going to refer to whether or not there is resonance stabilization. D and I are going to stand for dipole stabilization. A dipole stabilization, its technical name is inductive effect, so that's where that I is coming from. And then O comes to orbital, thinking about our hybridization, sp versus sp2 versus sp3. When we're thinking about this mnemonic, the things that are on the top are the most important. Charge, atom, and resonance are a lot more important than things like your dipole or your orbital. So in general, we'll kind of start with C, make a comparison, and then go down to A, make a comparison, go down to R, and you just keep going until you finally find a point of difference. And we're going to get a ton of practice in our class and our Friday review sessions on these. I want to talk about each of these in a little bit more detail, though. So C is for charge, and charge structures are going to be ones that have really, really low pKa's. So if you can have an oxygen or a nitrogen that has a positive charge, when that H gets abstracted and that lone pair goes back to that atom, it's now going to be neutral. And when we're thinking about like our major contributors to resonance, for example, from our last unit, things that are neutral are going to be way more stable than things that are charged. Those are going to be our major contributors to resonance. Same thing here. If you have things that are neutral compared to things that are charged, our neutral species are going to be way better than our negative species in terms of stability. So if your original structure carries a positive charge, that's going to be a lot more acidic protons connected to that atom compared to things that are neutral. Next, we'll think about atoms. And these are going to be thinking a lot about trends in electronegativity. So if we think of our periodic table and we look along our periodic table where we have like carbon, nitrogen, oxygen, and fluorine, we know that our electronegativity is going to increase as we go to the right. Fluorine is going to be more electronegative than oxygen. Oxygen's more electronegative than nitrogen. Carbon is the least electronegative of that series. So when you're thinking about the conjugate base that will form when that H gets abstracted, that's going to be a lone pair on whatever that atom is, our carbon, our nitrogen, our oxygen, or our fluorine. Atoms that are more electronegative can carry that negative charge a lot more favorably. So an oxygen with a negative charge is way more happy than a carbon with a negative charge because it's more electronegative. That's very similar to rules that we think about with resonance. When we're thinking if you had like a negative charge, you don't want that negative charge as a carbon ion. We want to move that over to the oxygen because the oxygen is more electronegative. Exact same reasoning here in terms of our stability. Now, in general, if you have a charge, and you'll have a charge a lot of the times, you'll have a lone pair carrying a negative charge. If that charge is stuck on one atom, that single atom needs to carry all of that weight of that charge. If you can spread out the load to multiple different atoms, that is going to help a ton in terms of stability. So there are two ways in which you can spread out that load. One is through resonance. The second is through the inductive effect, and that's through dipoles. Resonance is better. The inductive effect has a smaller impact. So in terms of resonance, if we think of, for example, two different alcohols here, our first through a carboxylic acid and our second here just as an alcohol. I have pK values underneath each of those, and you'll see the pK value of our carboxylic acid is around 5. Here it's 4.75. And the pK here of our alcohol is 15, right around water, which makes sense because it's very similar to water, just has a carbon rather than a hydrogen on the left side there. Now we'll see that there's a really, really big difference in the pKa, and we'll see that our structure here on the left has a significantly smaller, 3 times divided by 3 in terms of size for our pKa, meaning that in terms of our acidity, this proton here that we highlight here in yellow is way more acidic, and that's going to be removed much quicker and easier compared to the H of our alcohol in the second structure. One of the reasons for that is if we think and we do an acid-base reaction. So here we'll just show what our conjugate is. If you get a conjugate base like this, this charge here is not stuck on that oxygen because of resonance. I can show a resonance structure where this lone pair comes in to make a double bond, and then I have an adjacent double bond that can move to make a lone pair. And this negative charge, instead of being just stuck on this oxygen, can actually be spread across these 3 different atoms. So it can kind of share that load, and that's why it's a lot easier to remove that proton, because you're going to have a significantly more stable conjugate base. So that is going to be able to physically move the electrons in our conjugate base to help stabilize. The inductive effect is kind of like the same idea, but instead of just physically moving, it's just kind of pulling through a dipole. So, for example, if we look at our original carboxylic acid that we showed above that had a pK of 4.75, if way over here on this pink dotted carbon, right now it originally has 3 hydrogens. If I replace all 3 of those hydrogens with chlorine, chlorine is on the right side of our periodic table. As you move to the right and up of your periodic table, you're going to increase your electronegativity. That's going to help create dipoles, which are going to be pulling electron density towards that atom. In this case, if I replace all of those H's with chlorines, you'll see that our pK drops a ton, meaning that the H here is way more acidic and a lot easier to remove. And that's because of the dipoles that are from all of our chlorines. They are going to be pulling electron density towards them, and that's going to help spread out the load. So instead of the load just being trapped on these 3 atoms through resonance, it can also be partially shared just purely by pulling through the, this is known as the inductive effect, through these dipoles. You can help spread out the load. Now, you're not actually physically putting a charge, for example, on the pink carbon or any of those chlorines, and that's why it's weaker than resonance. But that is a way to stabilize. In general, we can kind of think about a handful of things. The more electronegative atom, the better. So fluorine is going to have a larger impact than chlorine. The more atoms, the better. So if you have 3 chlorines, that's going to be more acidic than something that only has, for example, 1 chlorine. And then also the proximity. If you have a molecule that's super, super big, and then on one side you have a proton, and then way on the other side you have like a atom that's causing a dipole, like for example, like a fluorine. If it's super far away, its impact's going to be really, really small. So the closer to that H, the better. The last part of our cardio is going to be O. If everything else ties, so if you have same charges, if you have everything that would go to the same atom, there is no resonance or all the resonances are the same, there is no inductive effect or all the inductive effect are the same, our final tiebreaker is going to be thinking about orbitals. When we think about our orbitals, and especially when we draw our energies, so if you have like a 1s, 2s, 2p in terms of energies, all the way back from like Gen Chem, our s orbitals have lower energy, and that's going to make them more stable. So if we think of our 3 different types of hybrid orbitals, our sp3, our sp2, and our sp, in our case of our sp3, if we think about how much s character there is, or how much of the s orbitals contribute to those hybrid orbitals compared to the p, you get about 25%, because you have 1 s for 4 total orbitals, 3 of the other ones being p, where here in your sp, that is 50% s character and 50% p character. So that's going to have lower energy compared to our sp3, and that's going to help stabilize. So a alkyne, which is going to be a triple bonded carbon, this H right here will be a little bit more acidic than like ones on a double bond or a single bond. These are going to be the really big tiebreakers. If you have something on a carbon, it's not going to be super acidic, so it's not going to be one that's going to win out very often. And those are kind of purely thinking about structures where you don't need to know pKs. You can just look at a molecule and think about, are there hydrogens that are connected to something that's charged or on a specific atom that's super electronegative? Is there resonance or inductive effect that can help stabilize? And then if nothing else, orbital. So in terms of our importance, these up here are more important than our orbitals. So we're thinking about importance kind of going upwards. And this is kind of a nice way where you can look at a structure and then know what's the most acidic proton without having to go through and memorize a bunch of pKa's. And we'll get a bunch of practice with this in class.